at your world line, and they end at the Big Bang and some finite distance. And what we're saying is that the greater inflation, the shorter that distance is. Right, that's what I just said. I could have pushed the button before. The distance along one of these geodesics to the Big Bang is a decreasing function of alpha. I'm reiterating. Okay, so in normal coordinates, the interpretation is each point was physically present at the Big Bang. The distance to the Big Bang is 0, but the time is, I mean, by definition, it's, you know, like if you fix the Robertson-Walker time, what is that? It's fixing the time since the Big Bang. Robertson-Walker what it means to be simultaneous in normal coordinates is backstage everyone starts their stopwatches and it's like, all right, Big Bang on 3. We're all going to stop our stopwatches in 13.7 billion years. And then they start their stopwatches and 13.7 billion years later they stop them, and whatever events you get that way, that's your Robertson-Walker simultaneity. So by definition then, there's this fixed time-like separation from the Big Bang. It happened some time ago, but 0 distance ago. In normal coordinates, events are separated from the Big Bang by an interval of time. In Fermi coordinates, the Big Bang is simultaneous to each event, and so instead you have this spatial separation, this rho and tau. That's the most satisfying interpretation I could get of it. And then, so in inflationary cosmologies, and at least to me now, it doesn't feel counterintuitive anymore that that spatial distance to the Big Bang would be less. That seems like a reasonable interpretation, just like the analogy in Robertson-Walker coordinates is like, for the amount of time you need to pass for a co-moving, like a proper distance to increase by a certain amount, goes down as alpha goes up. And so I feel like there's a good analogy there to that. So those were my concluding remarks. So that concludes what I have to say. I did make a separate presentation on all the intro manifold stuff, if you guys are really curious about manifolds now. But I do want to leave time for questions before people have to leave also. So, are there any questions?
I don't have a question. I have a comment in case you want to go on for a PhD.
Yeah.
The possible problem. This is a little out of the setup here, but David as well. It's very interesting. In algebraic geometry, I don't know if anybody else is familiar with this, there's a notion of a generic point of a variety. Okay, so variety is some solution of various equations in some space. And the generic point is a sort of a theoretical concept. And it has the property that it is in every open set of the variety. That reminds me of your Big Bang being in every Fermi space. So there's something going on there, and I'm wondering it would be interesting to see if you can put a topology on space-time in which the open sets are your Fermi space-times, and see where that leads. There may be something in common. Because the generic point would be the Big Bang. And that's in every open set, and see where that leads. That is an analogy, it's not that.
I'm not going to pretend I like, oh yeah, I'm totally there right now, but yeah, that sounds familiar.
But it's not. Yeah, it's not, I mean, physically, yeah, what does that mean? But mathematically, it's hardly far-fetched. It's sort of par for the course. It's been done. In a very different context.
Yeah. Sorry, I said no immediately because I was like, oh, you can't put a topology, but what I meant is you can't put a like metrizable topology.
Yeah.
Any other questions like that? That was awesome.
That was not a question, by the way.
Yeah, no, that's
suggestion for future research.
So how did working on this thesis affect your ideas of teaching middle school?
I know you and I have talked about this a little. I don't know, I feel like I am a much better teacher as a result of the entire process of grad school. The courses and just my understanding of mathematics, like even if I'd somehow, even without the actual process, if I'd just been like granted mathematical knowledge suddenly, that went from what I had before grad school to now, I feel like I would have been a better teacher immediately following that like addition of knowledge. somehow like understanding the really deep stuff allows me to understand the like basic stuff in a different way and present it in a different way. And I don't know, there's so much like, well, you can interpret the math this way, or this way, or this way, and that happens a lot. Like we're talking to other grad students, or like talking to myself, writing my thesis. There's all these different interpretations of things, and they're equally valid. And so when you're teaching, you often have to give a bunch of equally valid interpretations of the same mathematical idea until it clicks with how they already see the world. Right, guys? I have my honors geometry classes here. Yeah.
So this radius of the Fermi slice can be interpreted as the radius of the observable universe, correct?
Right, yeah, but in a weird way, because I mean you're sending out these space-like geodesics, and how like physically meaningful is a space-like geodesic? It's not what you would observe, because light travels on light-like geodesics. So you're sending out these paths that are not paths that light would travel on by definition. So it's not like what you're seeing, but neither really is the Robertson-Walker slices. So, sorry, I didn't mean to interrupt your question, but yeah, in a sense, yes. I mean, definitely it's art.
Okay.
One valid interpretation is that it is that.
Well, I mean, just to make it a little more concrete, if you have string, a very long piece of string, and you pull it tight in any direction as far as it will go, then it will go a finite distance, and the other end will hit the Big Bang.
Okay.
The string, the tight string is a geodesic.
Right. But like I started imagining the process by which you would pull it tight, and that imagining as a physical process, then it becomes hard to do that. You mean if you could just like instantly shoot it out? Or
If there was one.
right, okay. Oh, if it already existed.
Yeah.
Okay, yeah. Yeah. So it's weird. It does seem like
Yeah.
it is the universe.
Okay.
Guys? All right. Well, if there aren't any, and that was an hour, which seems like the right amount of time to do this. So, oh yeah.
Well, so
Yeah,
you're saying as the acceleration of the universe is larger than the radius of this observable, or the radius of the Fermi slice is going.
Yeah, exactly. Like if you look, here are t to the 1/2, t to the 1, and t to the 2. Like intuitively, this universe is expanding the fastest, followed by this one, followed by this one. But if you just draw a line across, that's your Fermi space slice. And so from here to here is the radius, and it's clearly the smallest here, then here, and then here. An interesting result that I didn't get to talk about is this is the space in which superluminal velocities are possible. Superluminal Fermi velocity. I didn't get to talk about velocity at all, but it's
Outside
in the
these
coordinates I
curves.
used, it's d rho d tau. Well, outside of the alpha equals 1.
Oh, okay.
Specifically. So you need a universe that isn't inflationary to have this space out here, and it's in these distances away from you that superluminal Fermi velocities are possible, which is another interesting result, but it's a whole new can of worms.
Right.
Bag of monkeys and
I mean,
animals.
I read somewhere that the radius of the observable universe is a lot larger than basically the speed of light times 3.7 million
Yeah,
years.
right. Yeah.
Or 13.7 billion years. So, because of inflation.
Right, yeah, but most of the time when people are talking about that stuff, they're talking in the standard Robertson-Walker coordinates, and so
Okay.
they're talking about, when they talk about a distance, that distance is measured along a geodesic in the slice they're taking that's not a geodesic in the ambient space, so it's like, is it really physically meaningful? Because yeah, it's an open question as far as I'm concerned in physics as to whether non-local superluminal velocities are possible. Local, no. In your local space, special relativity pretty much holds, and so you can't have a faster than light velocity. But if you go away far enough,
Right.
you can observe something going at a speed where if you were to bring it to where you were appears faster than your speed of light. Now, all those things are hard to define because, you know, space-time is manifold, and so the velocity over there lives in a different tangent spaces than velocities where you are. And so to compare them, you have to define the process by which you're going to compare them. And,
Right, so
there are
depending on
different ways
your
to do it.
coordinates or
Yeah,
point
depends
of
on a
view.
lot of things too, yeah.
the light traveling from some distant object in the edge of the observable universe might be interpreted as going faster than the speed of light.
Right, and yeah, if I understand what you're saying.
Can you go back slowly to the previous slide? There is one formula that I would like to go further.
Oh,
please.
all right, see.
I will stop you when you reach it.
Oh.
Can you go back? Yeah. Let me see here. No, further.
Further,
please.
okay.
Yeah.
Okay, again.
This is the proof.
Yeah.
Very
It's
further.
not an improvement,
Yeah.
okay.
That's it. Yeah,
No, this,
before that.
then we've got Leibniz rule, and then
There were this rho m tau, where you have an expression in terms of alpha and ts inside. You have this integral.
oh, okay, yeah, yeah. Right here. That one? No.
Yeah.
Or the one where we didn't replace it with
Well,
zero.
there is the ts.
Yeah, this-
Here, yes.
yeah.
So when you look at this formula, if you take your alpha, if you take an alpha less than 1,
Yeah.
and you take the ts going to 0, what happened? What will happen?
Oh, all right.
Is it going to blow up? No?
It does not, right. Yeah, you gotta find, yeah, right, you could see it in the picture, it was still, I mean, as alpha goes,
Yeah, this
at
is-
alpha
I'm
equals
asking
0,
because
yeah.
of the picture, right?
Oh,
This,
what's the limit as
I'm
alpha goes to
confused.
0 of it?
When ts goes to 0. For alpha, your picture is for alpha fixed, right?
Right. Oh, when TS goes to 0, that is actually, that's what we do here. And so that is how the picture was of this. So the picture was of when TS is 0. Is that the question you're asking?
Yes.
Okay, cool. Love when I answer the question someone's asking as opposed to other questions.
Okay.
It's fine.
Yeah, I'm fine.
Oh, thank you. Are
So
there any
this,
more questions?
this ugly expression that you had at the end, did you try to compute it numerically, evaluate it?
Which, there's tons.
The one?
The metric?
Yeah.
It was, that formula was already computed. The only thing I did was show that it was, like, it would be meaningless if we didn't know where Fermi coordinates held. I mean, they're you know, the theory of ordinary differential equations gives that there's some open set where they exist on, but like, if you don't know what that open set is, it's not really, it doesn't matter that much. And so what I did was just show where they're valid. The transformation formula was already known due to Dr. Klein and if I'm thinking of the right one from the metric G tau tau. Yeah. So, any other questions?
Well, that's, so we sign, right?
Yeah, if you want.
You didn't tell us, David, did he pass?